12 humans walked on the moon between 1969 and 1972. 6 landings, roughly 3.5 years. The longest stay on the surface lasted about 75 hours. And for more than 50 years since, no human being has set foot there again. In that silence, something quietly shifted. The moon we thought we had conquered turned out to be a place we had only briefly visited. Not understood, not mapped in any way that matters for living there. Just touched, for 3 days at a time, by men in suits built to survive a long weekend. And the moon, that decades of post-Apollo research has slowly revealed, is not the safe grey world of cultural memory. It is chemically reactive, electrostatically charged, radiation-soaked, seismically unstable, and thermally violent on timescales no Apollo crew ever stayed long enough to feel. If you are new here, welcome to Cosmio. Hit subscribe, pour something warm, and get comfortable, because tonight we are going to walk through everything those 50 post-Apollo years have taught us about the moon as a real physical environment, and the quietly unsettling question of whether humanity is actually prepared to return to it for good. Now, settle in and let's ease into this one slowly. Think about what you know about the moon. Really think about it. You can see it on a clear night without a telescope. You learned about it in school. You have seen the photographs, the grey dust, the boot prints, the flag. 12 human beings walked on it. All 12 came home. We brought back rocks, analysed the samples, wrote the textbooks. The moon feels like a solved problem. A place we visited, understood, and quietly filed away. But here is what the filing cabinet leaves out. 12 people walked on the moon between 1969 and 1972. 6 landings across roughly 3.5 years. And the longest any single crew spent on the surface, the absolute record for human time on the moon, was set by Eugene Cernan and Harrison Schmitt during Apollo 17 in December of 1972. They stayed for just under 75 hours. 3 days. 3 days is the longest any human being has ever spent on the moon. Not 3 months, not 3 weeks, 3 days. And then no one went back. For more than 50 years. Think about what 3 days actually reveals about a place. If you visit a city for 3 days, you learn where the good coffee is. You walk the main streets, you see the skyline, you come home and tell people you know the city, but you did not live through a flood season there. You did not drink the water long enough to notice what is in it. You did not feel the fault line beneath the city center shift under your feet at 3 in the morning. 3 days gives you the front room, the furniture you are allowed to see. It does not give you the basement. It does not give you the building's bones. We walked into the moon's front room 6 times, complimented the grey dust, and left before we ever opened a single interior door. The school book picture that came out of Apollo is not wrong in the way that a lie is wrong. The moon is genuinely quiet in certain ways. It has no weather, no oceans, no erosion from wind and rain. Those things are true, but a picture so incomplete that it leaves out the most important features functions as wrong. And the picture Apollo gave us left out almost everything that matters if you intend to stay. Because the real dangers on the moon are not the cinematic ones. Not a meteorite punching through a habitat wall, not an engine failing at liftoff. Those risks are real, but they are the kind of risks engineers can design against directly. The actual hazards are quieter than that. Slower, more patient. They are hazards that operate on timescales of weeks and months and years. Timescales no Apollo crew ever stayed long enough to encounter. The 50 years of silence after Apollo were not wasted. Robotic orbiters carrying instruments far more precise than anything the 1970s could build mapped the surface in detail no astronaut boot had ever reached. Apollo samples that had been catalogued and shelved were pulled back out and reanalyzed with laboratory technology that did not exist when they were collected. Long-term simulations were run. And crucially, people started asking questions that no one had thought to ask in 1972, because no one in 1972 was planning to live there. The question was never, during Apollo, how does this place behave over the course of a year? The question was, how do we survive the next 3 days and get home? Those are different questions. They have different answers. And the answers the last 50 years have produced are not reassuring. The moon that emerges from post-Apollo science is chemically reactive at the surface level. It is electrostatically charged in ways that cause fine particles to behave unpredictably. It is soaked in radiation that Earth's magnetic field normally deflects before it ever reaches the ground here. It is seismically active in ways no one expected. And it swings between temperature extremes so violent, hundreds of degrees in either direction across a single lunar day, that materials and structures must perform perfectly through thousands of those cycles just to last a year. None of that appeared clearly in the Apollo data. Not because Apollo was careless, because 75 hours is not enough time for any of it to show. Here is what makes that worth sitting with. The Apollo crews were not just skilled and brave, they were lucky. Quietly, unmeasurably lucky in ways that only became clear later. They flew during periods of relatively low solar activity, which meant the radiation environment was calmer than it sometimes is. They landed on flat, geologically stable ground, chosen precisely because it was safe. Their stays were so short that none of the slow accumulating hazards, the dust building in the equipment, the radiation dose climbing in the bloodstream, the material fatigue from thermal cycling, had time to reach a level that mattered. And when they were done, they came home to Earth, to the atmosphere, to the planet's magnetic field, wrapping invisibly around every living thing like a shield they had never once had to think about. To ground that does not shift in the same way. To air that requires no machinery to exist. That lucky combination of conditions will not be available to the crews who go back. The plan is not for 3 days, the plan is for weeks, then months. Then a permanent base, inhabited by rotating crews, indefinitely. And the chosen site is not one of the flat, sunlit, geologically quiet plains that Apollo selected for safety. The chosen site is the lunar South Pole. The reason is water ice. Craters near the lunar South Pole are so deep and angled that sunlight has not touched their floors in over 2 billion years. 2 billion years of permanent shadow, permanent cold, temperatures far below anything experienced anywhere else on the moon. And in that frozen, lightless isolation, water ice has accumulated and remained undisturbed. It is there. We have confirmed it. Ice that can be melted for drinking and split into hydrogen and oxygen, which becomes breathable air and rocket propellant. The South Pole offers the closest thing the moon has to a supply depot. That is why it was chosen. But here is where it gets strange. The features that make those craters uniquely valuable are the same features that make them uniquely dangerous. The permanent shadow, the permanent cold, the permanent isolation from sunlight. Those conditions are not an inconvenience alongside the prize. They are the same thing as the prize. You cannot have the ice without the permanent darkness. You cannot have the water without the temperatures that would kill an unprotected person in minutes. You cannot have the fuel source without operating inside an environment that may be among the most hostile on any solid surface in the solar system. The prize and the hazard share an address, and that is only where the list of hazards starts. Let's begin where every Apollo crew began, with the dust under their boots. The moment an astronaut stepped onto the lunar surface, the dust problem started. It coated suits from the boot soles to the helmet visor. It worked its way into equipment joints and jammed them. It scratched visors badly enough that by the second day of surface operations, vision through the glass had measurably degraded. It found its way into sample container seals and refused to release. Every crew reported the same thing. You brushed it away and it came back harder. The dust bonded to fabric, to metal, to the glass of instruments, to skin. It did not shake loose, it clung. But the real problem was not outside on the surface. The lunar module had no airlock. There was no chamber to pass through, no decontamination step, no way to leave a dust-coated suit behind. Astronauts climbed back inside with everything they had worn on the surface, sealed the hatch, and pressurized the cabin. And that was when something unexpected happened. The dust met oxygen for the first time in billions of years. It met moisture, it met warmth, and it reacted. Every Apollo crew described the same smell filling the cabin at repressurization. Burnt gunpowder. Not something chemical they had brought with them. Not a mechanical odor from the spacecraft. Burnt gunpowder. What they were smelling was ancient lunar soil waking up chemically. Material that had been frozen in airless, lightless, moisture-free conditions since before life existed on Earth was suddenly exposed to the conditions of a living environment, and it responded. That smell was a chemical event. The crew had no way to know, in the moment, exactly what was being released into the air they were breathing. Harrison Schmitt found out within hours. Schmitt was the geologist on Apollo 17, the only professional scientist to walk on the lunar surface. He was also, by any measure, one of the most physically capable human beings alive. Like every Apollo astronaut, he had been selected through a filtering process that eliminated nearly everyone. Peak physical condition was the baseline, not the achievement. Within hours of repressurization, his eyes were burning. His sinuses swelled shut. He could not stop sneezing. The symptoms were severe enough that the medical team named what he was experiencing lunar hay fever. It lasted for days. Other crew members across different Apollo missions reported scratchy throats, watery eyes, congestion that did not fully clear until well into the return journey, hundreds of thousands of miles from the moon. These were not people prone to illness. They were test pilots and fighter pilots. A few hours of exposure in a sealed but pressurized cabin had made them sick. Those exposures were brief. Hours of dust in the cabin, not days, not weeks. The long-term effects were never tested because no mission lasted long enough to test them. The question of what that dust does to a body over time was left unanswered. To understand why the question is serious, you have to understand what lunar dust actually is at the physical level. And it is not what the word dust suggests. On Earth, dust is old. Wind has tumbled particles against each other for millions of years. Water has smoothed their edges. The particles your respiratory system evolved to handle are rounded. The shape matters enormously. Your airways are built for round things. Cilia and mucus and the mechanical design of your throat and bronchial passages are all tuned to intercept and expel particles that have been softened by geological time. The moon has no wind. It has no water. It has no smoothing process of any kind. What it has had for 4 billion years is micrometeorites, tiny impactors arriving constantly from space, striking the surface at enormous velocity, shattering the top layer of rock into finer and finer fragments, not rounding them, shattering them. The result is particles with jagged, angular edges, tiny pieces of broken glass, cut at the molecular scale, never worn smooth, never softened. Edges sharp enough to cut tissue at the cellular level. Some of those particles are smaller than 1 micron across. A human red blood cell is roughly 7 microns. The smallest lunar dust grains are smaller than your blood cells. Particles that size do not stop in your throat. They do not get caught in the fine hairs of the nasal passage. They bypass every defense the upper airway has and travel deep into the alveoli, the tiny air sacs where oxygen passes into the bloodstream. Once there, they embed in tissue. And they do not leave. They are too small to cough out. They are too sharp for the body's natural dissolution processes to break down. They are chemically too alien for the immune system to recognize and neutralize. The body mounts a response. The particles do not care. They stay, and they keep cutting. NASA formed a dedicated research group specifically to study this. The Lunar Atmosphere Dust Toxicity Assessment Group. Their findings were not reassuring. The dust contains silicate compounds, the same class of minerals that cause silicosis in coal miners and quarry workers. Silicosis is a progressive lung disease. Scar tissue replaces healthy tissue. The scarring does not reverse. There is no cure. Miners who developed it did so through years of occupational exposure in open air with ventilation. The dust also contains something else. Embedded inside the glassy shells of the soil grains are nanoscale iron particles. These are chemically reactive. On contact with living tissue, they can trigger oxidative stress, a process of cellular damage driven by reactive oxygen species. The harm is not just mechanical, from sharp edges, it is also chemical, from inside the grain itself. One study from the University of Technology Sydney examined lunar dust simulants and found they were actually less toxic than the air quality in downtown Sydney on a bad day. Some researchers have cited this as evidence that the concern may be overstated. Here is why that comparison fails completely. Sydney residents breathe that air outside. They move through it. They leave it. Their lungs are not sealed inside a small pressurized chamber, with no filtration, no airlock, no way to wash the dust from their environment, and no exit for weeks or months at a time. The relevant variable is not the toxicity of the particle in isolation. The relevant variable is cumulative sealed cabin exposure with no mechanism for relief. Apollo had no HEPA filters. It had no airlock. There was no way to wash a suit. Every grain of dust brought inside the lunar module stayed inside the lunar module, suspended in cabin air, recirculated, breathed again. Future missions will not be measuring dust exposure in hours. They will be measuring it in weeks. And then there is the other problem. The one that makes every piece of existing research about lunar dust less complete than it seems. Every Apollo landing site was in the equatorial region. The dust those crews encountered had been exposed to sunlight for billions of years. Solar ultraviolet radiation had been interacting with its chemistry throughout that entire time. The South Pole, the Artemis target, is different. The dust inside those permanently shadowed craters has never seen sunlight. It has never been exposed to solar UV charging. Its chemistry, its reactivity, its grain structure, and its biological effects on living tissue have never been sampled, never been tested, and are entirely unknown. We are planning to build a habitat in a place whose dust we have never analysed, and the dust is only the beginning. What we have learned, slowly, over the decades since Apollo, is that the dust does something else entirely. Something the Apollo crews never fully understood while they were living through it. Something that changes the nature of the hazard from a surface contact problem into something closer to a weather system. The dust on the moon does not just sit there waiting to be kicked up. It lifts itself off the ground. Not because of wind. There is no wind. Not because of vibration or motion. Most of the lunar surface is absolutely still. The dust rises on its own because the moon is an electrically active environment, and the smallest particles are caught inside that electricity like flecks of metal near a magnet. Here is the mechanism. The moon has no atmosphere to filter incoming radiation. Sunlight strikes the surface whole and unfiltered, including all the ultraviolet wavelengths that Earth's atmosphere blocks before they reach the ground. When those UV photons hit the surface, they knock electrons free from atoms in the top layer of soil. This is the photoelectric effect, the same physics that earned Einstein his Nobel Prize. The surface loses electrons. The surface becomes positively charged. The smallest dust particles, the submicron grains, the same ones that slide past the airways and embed themselves deep in the lungs, pick up that same positive charge. And now you have two things sharing a charge. The surface is positive. The smallest grains are positive. Same sign charges do not attract. They repel. The grains lift off. They hover above the ground in a faint, invisible cloud of suspended razor-sharp glass, too fine to see, too small to feel, drifting in an airless silence above the surface of the moon. Here is where it gets strange. How high do they go? The models disagree. Some researchers believe the levitated particles hover within a few meters of the surface, a thin carpet of floating glass just above the ground. Others argue the layer could extend several kilometers upward, a faint envelope of charged dust wrapping around the entire day side of the moon. The numbers are not settled. No instrument has yet been placed on the surface specifically to measure dust levitation in real time across a full lunar day-to-night cycle. The heights are estimates built on theory, not confirmed by direct measurement, but there is observational evidence that something is happening up there. During the Apollo missions, astronauts in orbit noticed something they could not explain. Just before local lunar sunrise, along the edge of the shadow where day met night, they saw a faint shimmering glow along the horizon, a soft luminescence at the terminator, the moving line that divides the sunlit side of the moon from the dark side. It should not have been there. On a world with no atmosphere, there is nothing to scatter sunlight into horizon colors. There should be nothing glowing at the edge of the shadow, and yet it was there. The best current explanation is that what they were seeing was sunlight scattered by a thin cloud of electrostatically levitated dust hanging above the terminator. The Apollo crews were the first human beings ever to observe this phenomenon, and they did not know what it was at the time. They described it and moved on. Decades later, the physics caught up with the observation. Now let's think about the terminator itself, because what happens at that boundary is not simple. The sunlit side of the moon is positively charged, stripped of electrons by UV. The dark side is negatively charged. The solar wind, the constant stream of electrons and protons flowing outward from the sun, deposits electrons onto the surfaces it reaches. The night side sits in that flow and accumulates negative charge. Across the terminator line, you have two strongly opposing charges facing each other across a short boundary. That creates powerful horizontal electric fields. Fields that push not just upward, but sideways. And that matters more than it might sound. Dust does not just levitate at the terminator, it gets pushed laterally, horizontally, swept sideways along the surface by an electric force that has no visible origin, no wind, no contact, nothing you could detect or feel. A slow electric dust storm, not driven by any weather, moving with the boundary between day and night. The terminator moves steadily across the lunar surface because the moon rotates. A full lunar day takes about 20.5 Earth days. That means the boundary between sunlit and dark crawls at roughly 15 kilometers per hour. Jogging speed. Slow enough to walk alongside. But it never stops. It moves continuously around the entire moon, and it drags a curtain of charged, airborne glass with it. Every moment, somewhere on the moon, the terminator is sweeping forward and the dust is moving with it. For a future habitat, the implications are not abstract. Invisible particles too small to see. An environment with no atmosphere to make them felt. No sensation of dust in the air, no grit, no sting, nothing to signal that anything is happening. And yet, the particles are settling onto equipment, coating solar panels, working into seams in habitat structures, drifting into ventilation passages with no resistance because there is no resistance. The dust does not need anyone to walk through it to become airborne. It is already airborne. It has been airborne the entire time. The habitat is embedded in a slow-moving cloud of electrostatically active glass that tracks the movement of the sun. Apollo astronauts dealt with dust because they walked through it and brought it inside. Future astronauts will deal with dust that comes to them. The distinction is not a small one. In the Apollo framework, containment meant being careful about contact. In the long-duration framework, the dust is part of the surrounding environment, continuously responding to solar conditions, lifting, drifting, settling, and lifting again. Research literature has a single word for this: dynamic. The moon's dust environment is dynamic. It is not an inert layer. It is an active system. What remains unknown is the scale, the density of the levitated layers. the exact height they reach under different conditions, how the distribution shifts as the terminator passes, how concentrations build up at boundaries and how quickly they disperse. The models produce different answers. The measurements to resolve them do not yet exist. A full cycle, real-time, surface-level measurement of lunar dust levitation across a complete day and night has never been done. The ground itself exhales invisible glass, and the full shape of what that means for anyone living on it is still being worked out. Look up now. The dust is behind you, lifting and settling in the slow electric breath of the surface. Turn your eyes upward instead, to the black dome overhead. On Earth, that sky is where the protection lives. Here, on the moon, the sky is where the exposure arrives. Earth runs two shields simultaneously, and most people never think about either of them. The first is the magnetosphere, an invisible magnetic field generated deep underground by liquid iron churning in the planet's outer core. That churning creates electric currents, and those currents generate a magnetic field that extends tens of thousands of kilometers into space in every direction, wrapping the entire planet in a structure that deflects charged particles arriving from the sun and from deep space. Without it, the solar wind would strip away our atmosphere over geological time. Without it, surface life would be impossible. We have never lived without it. It has been there for billions of years, and we have never had to notice it. The second shield sits on top of the first. Earth's atmosphere is roughly 100 kilometers of increasingly dense air, and that air absorbs and scatters radiation that makes it past the magnetic field. It is why solar ultraviolet radiation does not kill us in ordinary daylight. The atmosphere is not just air to breathe, it is a second layer of protection stacked onto the first. The moon has lost both of them. The moon once had a magnetic field. When the solar system was young and the moon's interior was hot, its small iron core was still churning, and it generated a global magnetic shield similar in principle to Earth's. That ended roughly 3.5 to 4 billion years ago. The core cooled. The churning stopped. The field died. Today, there are faint, patchy remnants of magnetism locked into the crust in scattered locations. But they are weak and local and offer no meaningful protection. The moon is, in the vocabulary of planetary science, magnetically naked. And the atmosphere? The moon's atmosphere is so close to a perfect vacuum that calling it an atmosphere is generous. It contains only the thinnest possible trace of gas, far too sparse to absorb or scatter anything. It provides no protection at all. So every particle, every photon, every energetic nucleus arriving from space reaches the lunar surface at full strength, full energy, completely unfiltered. Nothing stops it. Nothing slows it. It arrives as it was launched, from whatever corner of the universe sent it. Not all of that radiation is the same problem. There are two distinct categories, and they behave very differently. The first category is solar radiation. Ultraviolet light, X-rays and energetic particles from the sun. These are serious. On the unshielded lunar surface, they arrive in concentrations that would cause severe biological damage with prolonged exposure. But they are a known and manageable problem. Physical barriers stop them. A suit blocks solar UV. A habitat wall blocks it. A visor blocks it. The engineering is demanding, but it is understood. With sufficient protection, solar radiation is a hazard you can engineer against. The second category is different. Genuinely different, and this is where the problem stops being a question of engineering thickness and becomes something harder. Galactic cosmic rays are nuclei of atoms, mostly hydrogen and helium, but sometimes heavier elements, including iron. They have been stripped of all their electrons, reduced to bare atomic nuclei, and then accelerated to nearly the speed of light by the most violent events in the universe. Supernova shockwaves, dying stars exploding millions of years ago, flinging material outward at enormous velocities, and those particles have been traveling through the galaxy ever since, bouncing between magnetic fields in interstellar space, arriving from every direction continuously, day and night, with no dependence on what the sun is doing. A single galactic cosmic ray striking a human body does not stop at the skin. It passes through skin, through flesh, through bone, through organs, through DNA, leaving a trail of broken molecular bonds the entire way. Think of it the way a bullet tears through paper. The paper does not stop the bullet. The bullet does not slow for the paper. And the paper is left damaged in a long, torn line behind it. That is what a high-energy cosmic ray does inside a body, except the paper is DNA, and the torn line is broken strands. Cells repair damage. That is part of what cells do. But they do not repair all of it, and they do not always repair it correctly. A misrepaired DNA strand does not always kill a cell. Sometimes it transforms one. That is how cancer begins. But here is where it gets strange. The instinct is to build a thicker wall. More shielding means more protection. That logic works perfectly for solar radiation. It does not work for galactic cosmic rays. When a high-energy cosmic ray nucleus hits thick metal, it does not stop. It shatters the metal's atoms on the way through, and that collision produces a spray of secondary particles. Neutrons, gamma rays, charged fragments, all of them scattering inward through the living space in every direction. One incoming particle becomes dozens. The wall does not absorb the energy. The wall multiplies it. Thicker shielding produces more secondary showers. Not fewer, more. The protection becomes a radiation source. This is not a failure of a particular material. It is a fundamental property of how high-energy nuclei interact with dense matter. No material and no design has yet been proven to reliably shield humans from galactic cosmic rays during long-duration missions. Some approaches look more promising than others. Water absorbs secondaries better than metal. Hydrogen-rich plastics produce fewer cascades than aluminum. Proposals for electromagnetic shielding, essentially an artificial magnetosphere wrapped around a habitat, have been discussed. None of these have been tested at scale. None have been flown. The problem remains open. Astronauts aboard the International Space Station receive roughly 10 times the radiation dose of someone on the ground. That sounds alarming. But the ISS remains inside Earth's magnetosphere, which continues to deflect the worst of what the galaxy sends. On the lunar surface, that protection is gone. The full unshielded cosmic ray dose arrives every second of every day. There is no time off. There is no safe room to retreat to, and going underground only helps so much. The most energetic cosmic rays penetrate meters of solid rock. A bunker carved into the lunar regolith reduces exposure but does not eliminate it. The particles that have traveled across the galaxy for millions of years are not stopped by a few meters of compressed soil. For a crew living on the lunar surface for a year, the projected long-term consequences include a meaningfully increased lifetime cancer risk, possible damage to the central nervous system, possible cardiovascular effects, and changes to the gut microbiome that could compromise immune function over time. Animal studies have shown cognitive decline after exposure to simulated cosmic ray environments, memory effects, decision-making changes, appearing not immediately but months after the exposure ended. Whether those findings translate directly to human crews at lunar dose rates is still being studied. The debate is not settled. The dust is a hazard you can see and feel and track. The radiation is something else. It arrives without color, without temperature, without sound. It does not register on any human sense. It passes through walls. It passes through bodies. It accumulates invisibly in tissue over weeks and months and years. And the engineering response to the hardest part of it does not yet exist. That is what arrives from overhead. Every second the moon has no sky to protect it. And radiation is only one of the reasons long-term habitation on the lunar surface is harder than it appears from the outside. Set that constant background aside for a moment, because there is another kind of radiation that does not wait at all. The cosmic rays discussed in the previous section are the steady accumulation. They are always there, always arriving. building dose like interest on a debt, slowly, invisibly, over months and years. What follows is different in almost every way. It is not slow. It is not constant. It gives almost no warning, and on a bad day, it can kill you in hours. The sun is not a stable object. That is easy to forget from where we stand. From Earth, it looks dependable. It rises, it crosses the sky, it sets. But the surface of the sun is a tangled, violent system of magnetic field lines, threading through superheated plasma, twisting under their own tension until they snap. When they snap, the release can be catastrophic. Enormous amounts of energy erupt in moments. These are called solar particle events. Some of them are relatively minor. Some of them blast waves of high-energy protons outward through the solar system at roughly 1/3 the speed of light. At that speed, those protons cross the distance between the sun and the moon in under 30 minutes. Think about that window. 30 minutes. On a good day, a satellite detects the eruption, ground controllers read the alert, and the crew has time to get inside. On a bad day, the crew is 2 kilometers from the habitat, in the middle of a geological survey, connected to their controllers only by a radio signal that may or may not reach the bottom of a crater. The 30-minute window assumes detection works, communication works, and the terrain cooperates. It assumes the rover starts. A spacesuit offers almost no protection against a serious solar particle event. That is worth saying plainly because the suit looks substantial. It is designed for vacuum, for temperature extremes, for micrometeorite dust. It is not designed to stop a wave of high-energy protons. Against a major event, the fabric does almost nothing. The crew is wearing the equivalent of street clothes in a rainstorm made of charged particles moving at 1/3 the speed of light. The dose magnitudes involved are not subtle. A major solar particle event can deliver several sieverts to an unshielded person over the course of hours. A sievert is a unit of radiation absorbed by biological tissue, weighted for how damaging that particular type of radiation is to the body. One sievert brings radiation sickness, nausea, vomiting, fatigue, a measurable crash in immune function. At 4 to 5 sieverts, roughly half the people who receive that dose will die even with medical treatment. Above 6 sieverts, survival becomes unlikely. Above 10 sieverts, it is nearly impossible. The Apollo program was not engineered against these numbers. No shielding system was designed to handle a major solar particle event during a lunar surface stay. The crews were protected by something else entirely. They were protected by luck. The missions flew during periods when the sun happened to be quiet. No major event struck during a transit. No event struck during a moonwalk. The timing worked out. And the crews came home. And the public understood that to be a function of skill and engineering and careful planning. It was skill and engineering for most of the hazards. For this one, it was timing. The direct evidence of how thin that luck was comes from a single date. In August of 1972, one of the most powerful solar particle events recorded in the 20th century erupted from the sun and swept through the space between the Earth and Moon. The estimated unshielded dose for an astronaut caught in open space during that event exceeds 10 sieverts. Not a concerning dose, not a dose requiring careful monitoring and medical observation after return. A lethal dose. Apollo 16 returned to Earth in April of 1972. Apollo 17 launched in December of 1972. The August storm hit the gap between them. A few months of different timing in either direction, and a crew would have been on the surface or in transit when it arrived. The astronauts who flew those missions did not know how close they had come. The public did not know. The calculations only became fully clear after the Apollo program ended. When they did, they were sobering enough to change how NASA thought about radiation planning entirely. Here is the contrast that matters for what comes next. Astronauts aboard the International Space Station face solar particle events as a known risk, but they sit inside Earth's magnetosphere. That magnetic field deflects much of the incoming proton wave before it reaches the station. The station also has designated shelter areas, sections with additional shielding where crews can ride out a storm, with reduced exposure. The magnetosphere does most of the work. The station's engineering does the rest. Doses from even significant events remain manageable. On the Moon, the magnetosphere is gone. There is nothing between the incoming protons and the surface. A solar particle event of the same magnitude that the ISS crew weathers, with minor added dose, arrives at the lunar surface at full intensity, unreduced. If a crew is outside when it arrives, their option is one: reach the habitat as fast as possible and hope the walls reduce the dose to survivable levels. If they are far from the habitat, that option closes. If the rover fails, that option closes. If the terrain blocks the radio signal and the warning never reaches them, they learn about the event when they begin to feel it, which is not the same as having 30 minutes to respond. In that case, they wait. The event passes when it passes. A major solar particle event can last hours, some last days. The Sun follows an approximately 11-year cycle of activity. During solar maximum, solar particle events are more frequent and more intense. The Artemis missions are being planned during a period that includes solar maximum conditions. That was not a scientific choice. It was a consequence of budgets and engineering timelines and political decisions made over the course of years. The schedule was set, and the solar cycle was not consulted. Mitigation strategies exist on paper. Thick regolith walls, buried habitats, improved early warning satellites to extend that 30-minute window. All of it is real engineering. None of it has been built and tested on the Moon. Regolith shelters exist in design documents. The solar monitoring satellite network needed for reliable warnings is not complete. The current state of radiation protection for long-duration lunar habitation is, in most respects, theoretical. The Apollo astronauts were brave. They were among the most capable people ever selected for a mission. And they were lucky in a way that was invisible at the time and only became legible afterward. For a crew spending weeks or months on the surface, the probability of encountering a major solar particle event does not stay small. It climbs. For a stay measured in months, encountering a significant event approaches certainty. The only questions become when it arrives, and whether shelter is reachable when it does, and SPEs are the hazard that announces itself, however briefly. The next set of problems on the lunar surface does not announce itself at all. Set the abrupt aside for a moment. SPEs are fast, violent, and at least briefly visible on the instruments before they arrive. What comes next is the opposite of that. It is patient. It is silent. It has no event, no warning, no single moment of impact. And Apollo never encountered it, not because of luck or planning, but simply because no crew stayed long enough. The problem is temperature. On Earth, temperature is something you manage with a thermostat. You adjust the dial, open a window, put on a jacket. The planet does most of the work for you without being asked. The atmosphere acts like a blanket wrapped around everything, trapping heat, distributing it, softening the edges of the daily cycle. Wind carries warmth from one place to another. Oceans absorb heat during the day and release it slowly through the night, smoothing the swings. Clouds intercept sunlight before it can hammer a single spot for hours. The result is that even in the most extreme places on Earth, the difference between the hottest moment of the day and the coldest moment of the night is roughly 70 degrees Celsius. In most places on Earth, it is far less than that. We call 70 degrees extreme. On the Moon, the daily temperature swing is 300 degrees Celsius. That is not a different point on the same scale. It is a different category of physical environment, and the details make it worse in both directions. During lunar daytime, the sun-facing surface climbs to around 127 degrees Celsius. That is hotter than boiling water. It is hot enough to damage electronics, warp metal, and degrade the rubber seals on any pressurized structure sitting in direct sunlight. But here is what makes daytime on the moon different from daytime anywhere on Earth. The lunar day lasts about 14 Earth days. The sun does not arc across the sky the way it does here. It moves slowly through a black sky and pours energy down on the same surface for 2 full weeks, with no atmosphere to diffuse it, no wind to carry any of that heat away, no clouds to offer even intermittent relief. Just 2 weeks of unbroken, unmediated radiation loading onto whatever is sitting there. Then the sun sets. On Earth, sunset begins a slow decline. The atmosphere holds warmth. The ocean releases what it has been storing. The temperature drops over hours, gently. On the moon, there is nothing to hold the heat. When the sun disappears, the surface radiates its stored energy directly into space, and the temperature crashes. Lunar nighttime surface temperature falls to roughly minus 173 degrees Celsius. That is colder than the deepest Antarctic winter, colder than liquid nitrogen, not slightly colder, dramatically colder. And that cold holds for another 14 days. The full cycle takes about 29.5 Earth days. 2 weeks of relentless baking. 2 weeks of bone-deep cold. Then it starts again. Apollo missed this entirely. The missions were short enough that crews landed in lunar daylight, conducted their work, and departed before experiencing even a fraction of a full thermal cycle. They never saw a sunrise that took 2 weeks to arrive. They never sat through 14 days of unbroken darkness at minus 173 degrees. Their equipment was never asked to survive even one full swing. A permanent base would survive thousands of them. This matters in ways that are easy to underestimate until you think about what heat and cold actually do to materials over time. Every bolt in a structure expands when it heats up and contracts when it cools down. On Earth, this happens every day. And the amplitude is small enough that most materials tolerate it indefinitely. But on the moon, the amplitude is 300 degrees per cycle. Heat the bolt, cool the bolt, heat it, cool it, for months, for years. Each cycle weakens the metal a tiny amount. The deformation is invisible. No impact happened. No force was applied from the outside. But the material is being slowly destroyed from within by the repetition itself. Engineers call this thermal fatigue. Thermal fatigue is one of the most reliable ways to destroy a structure without ever touching it. The cumulative effects spread through everything. Rubber seals that were airtight on day one begin to crack under repeated cycling. Welds, which are already the weak points in any fabricated structure, begin to split. Wiring insulation, which is typically some form of polymer, becomes brittle and crumbles. Lubricants inside motors and joints and hinges freeze solid during the cold phase and may not recover their properties fully when the temperature rises again. Joints that passed pressure tests before installation begin to leak by month 6 or month 7. Not because of any single failure event, because the structure was slowly, patiently destroyed by repetition. On Earth, thermal cycling is managed. Maintenance crews inspect equipment. Parts are replaced before they fail. Factories are reachable. If a seal starts to leak, you order a new one, and it arrives. On the moon, none of that infrastructure exists. Either you brought the replacement part with you, or you fix the problem with what you have, or you live with the failure and hope it does not cascade into something worse. The isolation makes every small material failure heavier than it would be anywhere on Earth. But the thermal problem is not limited to structures. It extends to power. Solar panels generate electricity when the sun is shining. During the 14-day lunar night, they generate nothing. A base that runs on solar power must store enough energy to survive 2 full weeks of complete darkness. The obvious solution is batteries, but batteries have a deep dislike of extreme cold. At minus 173 degrees, their chemical reactions slow dramatically, their capacity shrinks, and they may not function at all. Keeping the batteries warm enough to work through the lunar night requires energy. Generating energy is the problem you are trying to solve. The loop does not have an easy exit. Nuclear power systems have been proposed as one answer. A nuclear reactor generates heat and electricity continuously, regardless of whether the sun is up, regardless of the temperature outside. That independence is genuinely valuable. But reactors are heavy, which means they are expensive to launch, and every kilogram on the lunar surface costs something to get there. They require their own thermal management to avoid overheating their components. And they raise safety and maintenance questions that are especially difficult in a place with no emergency response capability. If something goes wrong with a reactor on the moon, the options available to the crew are the options they brought with them and nothing else. None of this has been solved. These are engineering challenges that are understood in principle and unresolved in practice. And then the South Pole adds another layer to all of it. The permanently shadowed craters at the lunar South Pole are the coldest natural environments ever measured in the inner solar system. The Lunar Reconnaissance Orbiter, a spacecraft that has been mapping the moon in detail from orbit, measured temperatures inside some of those craters as low as minus 248 degrees Celsius. That is only 25 degrees above absolute zero, the theoretical floor of physical temperature, the point at which molecular motion essentially stops. Think about that number, minus 248. In the context of the lunar surface temperature range the section has already described, that number is not merely cold. It is in a different regime of cold entirely. And these craters, these extraordinary frozen environments where temperatures approach the lowest possible limit, are the exact places where water ice is believed to exist. The permanently shadowed floors are cold enough to trap and hold volatile compounds that would evaporate anywhere else on the lunar surface. The reason we want to go to these craters is the same reason they are among the most hostile places in the solar system. Equipment designed and tested for the sunlit equatorial conditions of an Apollo landing would not survive minutes inside those shadows. The temperature alone would render most standard materials inoperative almost immediately. Sensors would fail. Seals would shatter. Lubricants would solidify. Electronics optimized for the survivable thermal range of the lit lunar surface would find themselves in an environment colder than anything they were built to tolerate. The thermal problem, then, is not a single issue. It is a layered set of constraints that touch power generation, structural integrity, materials science, and the specific geography of the places we most want to explore. The slow, patient work of repeated temperature swings does not produce a visible event. There is no flash, no alarm, no single moment of failure. There is only the structure becoming a little weaker with each cycle, the seal a little less airtight, the lubricant a little less reliable, until one day, the failure is no longer small. Thermal cycling is a weapon. It works slowly, and on the lunar surface, with no maintenance infrastructure and no resupply on demand, slowness is not the same as safety. And thermal cycling is one face of the engineering problem. The ground beneath the base presents its own. Go further down, beneath the surface, beneath even the regolith and its churning layers of glass and dust. Go deeper into the body of the moon itself, where a different process has been running quietly for billions of years. And what you find there overturns something most people assume without ever questioning. The common picture of the moon is this: volcanism ended billions of years ago. The interior has been cooling and solidifying since longer than complex life has existed on Earth. The surface is geologically frozen. It will simply sit there, patient and still, until the sun eventually swallows it. Nothing is moving. Nothing is changing. The moon is done. That picture is wrong. The moon is shrinking right now. As its interior continues to cool, it contracts. The entire body gets smaller. Over the last several 100 million years, the moon's circumference has decreased by more than 45 meters. On a body whose total circumference exceeds 10,000 kilometers, 45 meters sounds like nothing. A rounding error on a geological scale. And on Earth, it would be. Earth's crust is broken into large moving plates that slide, collide, and subduct, distributing stress continuously across the whole surface. When stress builds, The plates shift. Energy releases gradually. The surface flexes rather than shatters. The moon has none of this. Its crust is a single, rigid shell. One continuous piece of rock, wrapped around a shrinking interior. When the interior pulls inward and the crust cannot follow without breaking, stress builds with nowhere to go. And the only thing a brittle shell can do, when the body inside it shrinks, is crack. Think about what that cracking looks like from the surface. Sections of terrain get thrust upward and over adjacent sections, creating steep cliffs called lobate scarps. Lobate scarps, meaning crescent-shaped ridges, are the visible signature of a crust being compressed from inside. Some of them stretch for dozens of kilometers across the surface. Some have vertical faces rising tens of meters high. They are not subtle features. They are cliffs. And they are not ancient. Here is where it gets strange. The Lunar Reconnaissance Orbiter, which has been mapping the moon in extraordinary detail since 2009, has found thousands of these scarps. Many of them show surface features so fresh and sharp, so unblurred by micrometeorite erosion, that they cannot be more than a few tens of millions of years old. In geological terms, that is recent. Not ancient. Not left over from the early moon. Recent. The moon's crust is still cracking. The process is ongoing. And the cracking does not just reshape the surface, it generates moonquakes. Most people who know about moonquakes know only one version of them. The Apollo seismometers, left on the surface and recorded for several years before being switched off, detected quakes regularly. The picture that settled into public understanding was reassuring. Those quakes were deep, hundreds of kilometers down, caused by Earth's gravitational tug gently flexing the moon's interior. They were mild, not structurally threatening. The seismic signature of a world being slowly squeezed by a distant planet. That picture is incomplete. There is a second kind of moonquake, and it is not mild. Shallow moonquakes originate just a few kilometers below the surface, directly along the active fault lines created by ongoing contraction. They are not gentle. During the Apollo era, some of them reached magnitudes comparable to a moderate earthquake. Magnitude 5, strong enough to knock things off shelves, strong enough to crack walls, strong enough to damage structures not specifically engineered to survive them. A magnitude 5 earthquake in a city built to code is an inconvenience. A magnitude 5 moonquake beneath a habitat not yet built to any code, in a location where no replacement parts exist and no rescue is possible, is something else entirely. In 2024, a research team led by Thomas Waters of the Smithsonian Institution and Nicholas Schmer of the University of Maryland published a study that connected one of the strongest shallow moonquakes ever recorded directly to a cluster of young thrust faults in the lunar South Pole region, the same region designated as the Artemis crewed landing zone. They examined the candidate landing sites proposed for the mission and found that some of them sit uncomfortably close to active fault scarps. One site, called the Gerlasche Rim 2, is near enough to a young fault feature that the researchers flagged it explicitly as a concern in the published paper. Not in footnotes, not in supplementary material, in the paper itself. That was not all. In 2025, the same team reanalyzed data from the Apollo 17 landing site in the Taurus-Littrow Valley. Apollo 17 was the mission that carried the first geologists to the moon, the mission that collected the most carefully documented samples, the mission whose Valley of Landing is one of the most studied pieces of extraterrestrial terrain in history. Scientists had looked at the boulder falls and landslides visible in that valley for decades and concluded they were caused by meteorite impacts. That was the assumption. It was wrong. The reanalysis found clear evidence that those boulder falls and landslides would be seismically triggered, not by impacts, by moonquakes. The fault responsible, a feature called the Lee-Lincoln Scarp, has been generating magnitude 3 events repeatedly for the last 90 million years, and shows signs of remaining active today. A fault that has been cracking and slipping continuously beneath one of the most carefully studied lunar landing sites in history. And for 50 years, No one connected the landslides to the fault. The assumption of impact simply went unquestioned. The numbers that follow are precise enough to sit with for a moment. The probability of a damaging moonquake on any given day near an active fault is roughly 1 in 20 million. That sounds safe. For any single day, it essentially is. But probability accumulates over time, and a permanent lunar base is not a single day. Over a decade of continuous human habitation near one of these fault systems, the accumulated probability of a damaging quake rises to roughly 1 in 2,500. Better odds than being dealt 4 of a kind in standard poker. Not unlikely. Not edge case theoretical. It will happen. Only the timing is uncertain, and the faulting is not confined to the South Pole. By early 2026, scientists had catalogued over 2,600 small surface ridges distributed across the entire lunar surface, all formed by the same compressional forces driving the scarps. Every part of the moon is under the same stress. The shrinking is not localized. It is global. The crust is cracking from one end of the surface to the other, quietly and steadily, driven by the same cooling interior that has been contracting for billions of years and is still contracting now. The moon is not geologically frozen. It is geologically active on the only timescale that matters for a permanent human presence, our own. What that means for a crew sealed inside a habitat during a shallow fault rupture directly beneath them is a question the next section answers directly. Now let's stay with the shaking itself. Not where it comes from, what it actually does when it arrives. Start with what you know. An earthquake begins and it ends. The ground lurches, walls crack, things fall from shelves. It is violent and sudden, and then, usually within a minute, sometimes less, it is over. The fault has ruptured, the energy has released, and Earth's crust goes to work absorbing it. Water in the rock takes some. Layered geology scatters more. Loose soil dampens the waves as they travel outward. Earth is wet, layered, and complex in ways that make it surprisingly good at swallowing its own violence. In the aftermath, there is silence, damage, and the slow work of assessment. A moonquake does not behave like that. Not even close. The first moments can be deceptively gentle. A shallow moonquake might begin so mildly you would not feel it through your boots. No sudden lurch, no dramatic first blow. You might think it was nothing. And then, it continues. The shaking builds, fades, builds again. Not because the fault is still rupturing. The rupture may have ended in seconds, just as it would on Earth. The shaking continues because the energy has nowhere to go. The moon's crust is bone dry. There is no groundwater. No water in the rock to absorb the passing waves. And the rock itself has been shattered over billions of years of meteorite bombardment into a fractured blocky structure that reflects seismic energy rather than absorbing it. The waves bounce back and forth through the crust, losing almost nothing with each pass. The energy trapped, cycling, going nowhere. The Apollo seismometers captured this directly. A moonquake would register on the instruments, and then it would keep registering. The signal would not taper off the way earthquake signals do. It would ring, slowly diminishing, for over an hour before the ground finally went quiet again. An hour of continuous vibration from a single fault rupture. The scientists who first saw those readings thought the equipment had failed. That conclusion was reasonable. Earth instruments do not produce readings that look like that. Earthquakes do not behave like that. The shape of the signal was so unlike anything they had seen that malfunction seemed more plausible than the alternative. The instruments were fine. The moon simply rings like a bell when struck, and keeps ringing. Sound echoing in an empty stone cathedral, reflecting off hard surfaces with nothing soft to absorb it, going around and around until it finally fades on its own. Now place a human habitat in the middle of that ringing. Pressurized structure, bolts, welds, seals, gaskets, all engineered to precise tolerances. Everything connected, everything relying on everything else holding its position and maintaining integrity. What does an hour of continuous vibration do to a system like that? The effect is cumulative. A bolt that would survive a brief seismic event can be worked slowly loose by prolonged vibration. It backs out of its thread. Not all at once, not in a single dramatic moment. A fraction of a turn per cycle. A gasket that holds through a short shake can shift position under an hour of sustained movement. A seal that was flush before may not be flush after. Hairline cracks appear in components that were intact when installed. None of these failures announce themselves loudly. They accumulate quietly, invisibly, the way thermal fatigue does, the way radiation damage does, building toward a threshold nobody can see until it is crossed. But the structure above the ground is not the only problem. The ground itself presents a separate hazard. The lunar surface is covered by regolith, a layer of broken fragments, ground-up rubble, and fine dust accumulated from 4 billion years of meteorite impacts. This layer extends to depths of several meters. It is not solid rock. The particles are not strongly bonded to each other. It is, in engineering terms, a deep accumulation of loose granular material. Under sustained vibration, loose granular material can do something that seems impossible if you have only seen it sitting still. It can liquefy and flow. The technical term is seismic settling. Each vibration cycle rearranges the loose particles slightly. The packing shifts. The surface level drops in some places, rises slightly in others, moves laterally in ways that no static survey would predict. What was flat becomes uneven. What was level shifts. The process is not dramatic from the outside. It is slow and quiet and continuous, and it happens beneath whatever is resting on top. A habitat foundation on regolith during a prolonged moonquake may find that the ground has moved by the time the shaking ends. A landing pad that was level before may not be level after. A habitat wall that was vertical when constructed may be leaning slightly when the dust finally settles. These are not hypothetical catastrophes. They are predictable consequences of placing rigid engineered structures on loose granular material in a seismically active environment. In 2024, the Waters and Schmerz study drew a direct line between the moon's ongoing contraction, the young thrust faults that contraction produces, and the shallow, high-magnitude moonquakes those faults generate. The chain of evidence was built from orbital imagery, Apollo-era seismic records, and new modeling of the lunar interior. The conclusion was specific and uncomfortable. The South Pole region is not geologically quiet. It is one of the most seismically active areas on the moon, and it is the region we chose for the first long-duration human presence. Then, in 2025, the follow-up work arrived. The boulder falls and landslides in the Taurus-Littrow Valley, the site of Apollo 17, the most extensively studied landing site in lunar history, had been seismically triggered. Not by meteorite impacts, as had been assumed for decades, by moonquakes. The Lee Lincoln Scarp running beneath the Apollo 17 site has been generating seismic activity for at least 90 million years, with no indication of stopping. Here is what that means. Apollo 17 was chosen partly because the site appeared stable. It was chosen by scientists who were careful, who looked at the available data, who made reasonable judgments based on what they could see. They were working with the best information available to them, and they were wrong about what lay beneath it. The question that follows is not comfortable. How many other apparently calm lunar landscapes are hiding active fault systems that no one has yet detected? We do not have a way to answer that question right now. The Apollo seismometers were switched off decades ago. The seismometer that was supposed to be delivered to the lunar surface by a recent mission never arrived. As of now, there is no real-time seismic monitoring of the lunar surface anywhere. Not a single working instrument on the ground. No continuous record. No early warning capability. No way to know what the ground has been doing since the last Apollo sensor went dark. We are planning to send people to a world where the ground periodically shakes for an hour at a time. where that shaking triggers landslides on crater walls, where the foundation material beneath any structure can flow and settle under sustained vibration, where the specific region chosen for habitation has been identified in peer-reviewed work as sitting directly above active fault lines. And we are planning to do all of that without a single working seismometer on the surface to tell us what the ground is doing between now and the first landing. The moon does not announce its intentions. There are no weather systems to read, no atmospheric pressure changes, no surface signs that give warning. It simply shakes, then keeps shaking, then waits quietly for as long as it needs to, and then shakes again. And the seismic hazard, as significant as it is, operates on a timescale a crew can at least conceptually track. The next hazard on the list does not work that way. It operates across weeks and months and years, too slow to feel in any single moment, too fast to ignore across a mission. Stay with that silence for a moment longer, because something else is happening inside it. The shaking you just read about is episodic. It comes at rings for an hour, and then the moon goes quiet again. But there is a second process running alongside it, and unlike the moonquakes, this one does not pause. It does not cycle. It does not wait. It has been going continuously, without interruption, for 4 billion years. Every second of every hour of every day, the lunar surface is being struck by particles arriving from interplanetary space, not occasionally, not in storms or seasons, continuously. This hazard almost never comes up in public discussions of lunar habitation, because compared to radiation and seismicity, it sounds minor. Dust, tiny particles, almost nothing. And each individual event is, in fact, almost nothing. That is exactly what makes it worth spending time on. Start with what Earth does for us, and does so silently that we have never had to notice. The atmosphere is not just air to breathe, it is physical mass. A column of gas roughly 100 kilometers deep presses down on every square inch of ground at about 14 pounds of force. That column is dense enough to do something extraordinary. It burns things. Any rock, any metal fragment, any piece of debris falling toward Earth must pass through that column. The friction is enormous. Small objects vaporize completely before they get close. Medium-sized objects break apart, burn, and fall as streaks of light across the sky. Only the largest, most robust pieces survive the passage at all, and even they arrive diminished. The atmosphere has been doing this quietly, on every square meter of the planet's surface, for billions of years. It is a planetary-scale defense system so effective that we built an entire civilization without once having to engineer around its absence. We simply never noticed it was there, because it never stopped working. The moon has no meaningful equivalent. The lunar atmosphere is so sparse it is effectively a perfect vacuum. Particles arriving from space encounter essentially no resistance, no slowdown, no burning. They simply continue at whatever speed they had through interplanetary space until they reach the ground. Here is where the numbers matter. Interplanetary space is not empty. It is threaded with debris from the early solar system, fragments from asteroid collisions, material expelled from comets, dust streams the moon passes through on its orbit. The smallest of these particles, sand grain-sized or smaller, are micrometeorites, and they arrive at the lunar surface moving at between 10 and 70 kilometers per second. 10 kilometers per second is 36,000 kilometers per hour. A military rifle bullet travels at roughly 3 kilometers per second. These particles arrive at more than 3 times bullet speed. The fastest of them arrive at more than 20 times bullet speed. When something that's small hits at that velocity, the energy released is extraordinary relative to its mass. The impact vaporizes both the incoming particle and a small amount of the surrounding surface. It creates a tiny crater. It sprays molten rock droplets outward in all directions. Those droplets cool almost instantly in vacuum and fall back to the surface as tiny glass beads. they add to the layer of glassy, jagged powder that already covers everything. The same layer already discussed in the context of dust. The regolith is not a passive remnant of the early moon. It is the accumulated product of this process, running without interruption for 4 billion years. Every square centimeter of the lunar surface has been struck countless times. This is how the regolith got there. For human presence, this stops being ancient history. It is happening right now. Every hour that passes, particles are arriving and striking whatever is on the surface. Ancient rock, a newly constructed habitat wall, a solar panel, a suit stored outside. The probability that any specific small area is hit in a given hour is low, but probability is patient. Structures of meaningful size, exposed over months and years, accumulate total strikes that become significant. And the greater threat is not the individual impact events. It is what those impacts do over time. Every exposed surface on the moon is being continuously sandblasted. That is not a metaphor. The constant rain of particles arriving at extreme velocities slowly abrades whatever it touches, pits the surface, scratches it, strips thin layers away, slowly and without pause. Apollo gave us the first direct evidence of how fast this happens, and the speed was not what engineers expected. After just a few days on the surface, the outer boot layers on Apollo suits showed measurable wear. Not theoretical wear extrapolated from models. Visible wear in 72 hours. Vacuum seals on sample return containers were damaged by abrasion to the point that some no longer sealed properly after a single mission. Equipment designed to precise tolerances showed wear inside 3 days of exposure. Not months, not years, 72 hours. Now extend that to a permanent base. Every surface facing the sky is being continuously abraded. Solar panels develop pitting and surface scratches that scatter light rather than capturing it, reducing efficiency over months. Optical instruments accumulate haze as external lenses are slowly ground down. Thermal insulation on pipes and cables is gradually stripped away. Habitat walls accumulate micro-impact after micro-impact. Each individually trivial, all of them collectively thinning the protective material between the people inside and the vacuum outside. On Earth, maintenance solves this. You replace worn parts. You repaint, reseal, swap components on a schedule. The systems for doing this are local, cheap, and fast. On the moon, every replacement part has to be manufactured on Earth, launched, survive the transit, and arrive at the right time. The logistics of maintaining a permanent structure against a continuous abrasion process of this kind have not been fully solved. Proposals exist. Robotic systems applying fresh protective coatings on a rotation, burying habitats under thick regolith layers to shield the top surfaces. Both approaches are plausible. Neither has been tested at scale in actual lunar conditions. But the micrometeorite problem and the dust problem are not two separate items on the list. They are the same cycle. Each micrometeorite impact kicks up fresh particles from the regolith. It exposes new sharp edges on buried grains. It adds new glass beads to the top surface. It refreshes the electrostatically charged dust layer that then lifts and drifts and settles onto everything nearby. The dust problem described in earlier sections feeds continuously from this source. Impact, fragmentation, electrostatic levitation, redeposition, running without interruption for as long as the solar system has existed. The moon is not a static surface waiting to be visited. It is an environment being continuously shaped by forces that will not slow for construction schedules or mission timelines. And the abrasion hazard is patient in the same way the radiation hazard is patient. In the same way, thermal cycling is patient. No single event announces itself as dangerous. The danger is in the accumulation, building invisibly across months and years toward thresholds that are difficult to predict and harder to reverse once crossed. The engineers who will design long-duration lunar infrastructure will have to account for a surface that is, in the most literal sense, slowly grinding itself down and slowly grinding down everything placed on it. The question of how to build things that last on a surface like this has not been answered. It has barely been asked at the scale that a permanent base would require. All of that hazard accumulates across the entire lunar surface, from the equator to the poles, from the near side to the far. Every square meter of the moon is exposed to micrometeorite rain, to radiation, to thermal cycling, to the possibility of a shallow moonquake rolling through loose regolith beneath a structure built to last. None of that changes depending on where you plant a habitat. But one place concentrates nearly all of it, and adds hazards found nowhere else on the moon. That place is the lunar South Pole, and it is exactly where we have decided to go. The reason is water. Specifically, water ice trapped in permanently shadowed craters that cluster around the pole. These craters are not simply cold and dark. They are so deep and angled so precisely relative to the sun that sunlight has never reached their floors. Not once. Not in over 2 billion years. The moon's axial tilt is almost perfectly upright compared to Earth's. At the poles, the sun never rises high into the sky. It skims along the horizon, throwing light across the tops of crater rims, but leaving the floors below in a darkness that has held, unbroken, since before complex life existed on Earth. In that eternal shadow, at temperatures that represent some of the coldest conditions measured anywhere in the solar system, water ice has accumulated over billions of years, delivered by comets and asteroids, preserved by cold, never once broken by warmth. The strategic value of that ice is difficult to overstate. Water sustains human life directly. It can also be split by electrolysis into hydrogen and oxygen, providing breathable air and rocket propellant. If rocket fuel can be manufactured on the moon from local resources, the cost and complexity of every mission that follows drops dramatically. Every kilogram of propellant that does not need to be launched from Earth makes the next step in space cheaper and more achievable. South Pole ice is not a scientific curiosity. It is potentially the foundation of everything that comes after. The logic of going there is powerful and clear. But the South Pole is also the most dangerous place on the moon, and the reasons stack in ways that matter. Start with the cold. The permanently shadowed craters are not just cold by lunar standards. The Lunar Reconnaissance Orbiter has recorded temperatures inside some of these craters as low as minus 248 degrees Celsius. That number needs context. Pluto, in the far outer solar system, averages around minus 225 degrees Celsius at its surface. The floors of some south polar craters are colder than Pluto. That is not a comparison you can set aside. These are among the coldest natural environments measured anywhere in the inner solar system, and the crater floors represent only 25 degrees above absolute zero, the theoretical point at which molecular motion stops entirely. No equipment designed for standard lunar surface operations was built for those temperatures. Materials that function reliably at minus 70 degrees Celsius, already the brutal cold of a regular lunar night, can fail completely at minus 248. Electronics behave in unpredictable ways at those extremes. Batteries stop functioning, and lubricants do not simply freeze. They become rigid solids with no lubricating properties at all. A rover that rolls smoothly on the lit surface becomes a fixed object the moment its mechanical joints reach those temperatures. No machine has ever operated in those conditions. There is no test data. There is no failure mode history. There is only theory, and the certainty that the conditions are unlike anything engineering has validated so far. The dust compounds the problem in ways that are harder to anticipate. Dust on the sunlit lunar surface has been sampled, analysed, and studied since the Apollo era. It has spent billions of years under continuous solar UV bombardment, subjected to electrical charging processes driven by sunlight and solar wind. The dust inside permanently shadowed craters has not. It has sat in cold, airless darkness, untouched by sunlight, untouched by UV, shielded from the same charging processes that shape dust behavior on the lit surface. Its chemistry may be completely different from anything Apollo crews brought home. It may contain volatile compounds, frozen gases trapped alongside the water ice. that would behave in entirely unexpected ways when disturbed by human activity. When a boot steps into that shadow for the first time and kicks up a cloud of material that has not moved in 2 billion years, nobody can say with certainty what that cloud is made of. Not roughly, not approximately, with any certainty at all. How it will react with a spacesuit, what it will do if it enters a breathing space. The questions are not theoretical concerns waiting for more data. They are unanswered at a level that makes planning around them genuinely difficult. The radiation geometry at the South Pole adds another layer. The crater walls do offer partial protection against solar particle events. A crew on the floor of a deep-shadowed crater sits below a rim that blocks some of the incoming proton wave from a solar storm. That is a real benefit. But galactic cosmic rays do not come from the sun. They arrive from every direction in the sky equally, pouring in from the full sphere of space above. Crater walls only block the portion of sky they physically cover. The rest remains open. But here is where it gets strange. Some estimates suggest that inside certain crater geometries, cosmic ray particles striking the crater walls are reflected and scattered back inward. The same walls that reduce direct solar exposure may concentrate scattered galactic radiation toward the center of the crater floor. A crew sheltering from a solar particle event could be sitting in a geometry that amplifies the background dose at the same time. Detailed modeling for specific south polar craters is still ongoing. The answer is not settled, but the possibility exists that the shelter creates the problem. The seismic picture at the South Pole is the one confirmed by recent research in the most uncomfortable terms. The 2024 Waters and Schmer study found that young thrust faults, active scarps, and shallow moonquakes linked to ongoing lunar contraction are concentrated in the South Pole region specifically. The dramatic landscape of the poles, towering crater rims, deep shadowed floors, fractured terrain, is dramatic partly because it is still being actively shaped. The same geological forces that built the cold traps where the ice accumulated also compressed and faulted the terrain through which any habitat would need to be constructed and anchored. The South Pole is not ancient and finished. It is the most seismically concerning area on the Moon for human habitation. And then, there are the operational hazards no mission has fully solved. Earth sits low on the horizon as seen from the lunar poles, and it dips below the horizon entirely for portions of every orbit. Direct line-of-sight communication with Earth is not continuous. Relay satellites in lunar orbit can bridge some gaps, but a complete and reliable communication architecture for the South Pole does not yet exist. During any gap in coverage, a surface crew is entirely on their own. No mission control, no real-time data uplink, no ability to call for assistance if something goes wrong at the wrong moment. Navigation presents its own set of unsolved problems. The equatorial sites Apollo visited were relatively flat and open. The South Pole is extreme contrast, razor-sharp crater rims flooded with permanent sunlight directly adjacent to crater floors in absolute darkness. Cameras saturate on bright ridges and go blind in shadowed floors, sometimes within meters of each other. Rovers built for gentle equatorial terrain would struggle with steep, fractured slopes and surface properties that have never been driven on, never been tested, never failed in a way that produced usable engineering data. The South Pole is not a gift. It is an exchange. We can have the ice if we accept the coldest temperatures in the solar system, unknown dust chemistry, unresolved radiation geometry, the most seismically active terrain on the Moon, communication gaps, navigation challenges, and equipment failure modes that have never been encountered, because no machine has ever operated in those conditions. Everything we want from the Moon is concentrated in that one place. So is everything we have not yet figured out how to survive? And the hazards discussed so far are the ones that apply specifically to the surface and the environment. There is another category of problem waiting, one that has nothing to do with dust or radiation or cold. It has to do with the body itself and what living in this environment does to the people inside it over time. Every hazard described so far has something in common. You can measure it. You can run it through a simulation, model it on a computer, build a test chamber and recreate some version of it on Earth. Dust particles can be imaged and analysed. Radiation doses can be calculated. Temperature swings can be replicated in a lab. Moonquakes can be studied through seismometer data and geological mapping. The answers are incomplete and in some cases genuinely unsolved, but science knows how to approach them. There is a framework. There is a method. Now turn the lens inward, not at the moon, but at the person standing on it. The human mind is not well suited to the lunar environment in ways that took researchers a long time to articulate precisely, because the hazards are harder to put in a dosimetry report. They show up in behavior, in sleep, in the slow fraying of judgment and mood over weeks and months. And they have received considerably less engineering attention than the problems that leave marks on metal. Start with silence. The moon is the quietest place a human being can go. Not quiet in the way a library is quiet, where there is always a soft ambient hum that the brain uses to orient itself in space and time. Not quiet the way a forest is at night, where there are insects and wind and the faint sound of settling wood. Moon silence is absolute. There is no atmosphere to carry sound waves. Nothing happening outside the habitat makes any noise inside it. You cannot hear micrometeorites striking the outer wall. You cannot hear temperature changes cracking metal joints. You cannot hear anything from outside at all. The only sounds are mechanical. The hum of life support. Your own breathing inside the suit. Your heartbeat. Your own voice. Researchers studying extreme isolation have documented what happens after days and weeks of this. Absence of natural sound does not produce peace. It produces something the brain experiences as hunger. A sensory deficit it begins trying to fill on its own. Sometimes with sounds that are not there. The brain is built for a world that makes noise. Remove the noise entirely, and the brain does not go quiet. It starts generating. The view offers something remarkable. Earth hangs in the black sky, bright and blue, 4 times larger than the full moon appears from Earth's surface. Stars do not twinkle, because there is no atmosphere to scatter their light. They are sharp and steady and present in numbers no Earth-based observer ever sees. By almost any measure, it is one of the most stunning visual environments a human could occupy. But the landscape beneath you is something else entirely. Grey, every shade of it. The ground, the rocks, the crater walls, the far ridgeline, all of it grey with no variation in colour. No texture that changes from 1 kilometre to the next. No trees, no water, no clouds, no movement of any kind except what you and your crewmates create. Every crater looks similar to the last. Every rock formation blurs into the previous one. The sky never changes. The sun moves so slowly across it that you cannot perceive the movement in real time. Days feel neither long nor short. They feel wrong. Researchers studying human factors in isolated extreme environments use the phrase time suspension to describe this. The normal cues that divide a day into meaningful segments, the brightening of early morning, the quality of afternoon light, the gradual cooling and darkening toward evening, none of them exist. Time becomes structurally featureless. And a structurally featureless day is one the brain does not know how to organize. Here is where it compounds. The 24-hour circadian rhythm that governs sleep, hormone production, immune function, and cognitive performance runs on environmental cues. On Earth, light changes across the day. Temperature shifts. Sound shift. The body reads all of it and synchronizes accordingly. On the moon, the lunar day is 29.5, Earth days long. Light does not change on any scale the human body can detect. Your body does not know what time it is. After weeks, it begins to show. Sleep disruption is one of the most consistently documented problems in space environments. Astronauts on the International Space Station, in a structured environment with carefully managed artificial lighting, still report poor sleep quality. On the moon, the problem is larger. The external cues that anchor human sleep, the gradual darkening of evening, the natural cooling of night, the sounds of a world settling toward quiet, none of them exist. Sleep must be managed entirely through artificial lighting and scheduled rest periods. Research suggests this works imperfectly, and chronically disrupted sleep does not simply make people tired. It degrades cognitive performance, slows reaction time, compromises emotional regulation, and weakens immune function. Each of those effects compounds across weeks and months. But here's where it gets strange. The psychological hazards do not arrive one at a time. Communication with Earth introduces a delay of roughly 5 seconds round trip, about 2.5 seconds each way as signals travel the distance. In ordinary conversation, 5 seconds is noticeable but manageable. In an emergency, 5 seconds is a different thing entirely. If something fails on the surface, the crew cannot turn to mission control for real-time guidance. By the time they describe the problem, wait for the signal to travel to Earth, and receive a response, 5 seconds have passed. Every critical decision must be made by the crew in the moment, without the option of calling for help in any meaningful real-time sense. That places enormous cognitive and psychological burden on a small team already managing the sustained stress of an environment that is actively working against their survival in multiple simultaneous ways. The team itself is small. Early lunar base crews will likely number between 4 and 6 people, living for months at a time in a habitat that, however well designed, will be compact by any residential standard. Personal space will be minimal. Privacy will be nearly non-existent. Every interpersonal tension, every personality conflict, every difference in communication style or work preference will be amplified by proximity, by stress, by fatigue, and by the complete absence of the option to simply go somewhere different and clear your head. You can go outside, but outside is the same grey moonscape in every direction, with a clock running on your suit's life support system, reminding you that you cannot stay out indefinitely. Research from Antarctic winter overstations, from submarine deployments, and from long-duration spaceflight simulations consistently shows the same pattern. An initial period of high motivation and cohesion. A middle phase marked by rising interpersonal friction and declining motivation. And what psychologists have named the third quarter phenomenon, a significant dip in mood and performance that clusters around the halfway point of a long, isolated mission. Recovery typically comes as the visible end approaches. On a permanent base, there is no visible end approaching. Rotation schedules change. Crew members arrive and depart. But the place does not end. The expedition psychology that produces the third quarter dip and the end recovery was built around the architecture of a temporary presence. A permanent base has no architecture of an ending. No one knows yet how those patterns shift when the horizon never moves. None of this means humans cannot live on the moon. People have endured conditions of extraordinary difficulty throughout history. The mind is more adaptable than it appears from the outside, but adaptation requires honest preparation. It requires acknowledging that the psychological challenges are as real and as serious as the engineering ones. We have spent decades designing suits, habitats, and radiation shields. We have spent considerably less time and resources designing psychological support systems, communication protocols, privacy architecture, and mental health frameworks that determine whether the people inside those suits remain capable of doing their jobs after 6 months of lunar grey. The moon is quiet. Deeply, completely, unrelentingly quiet. And that silence has a weight to it that no engineering specification has ever fully captured. The psychological environment is one category of inward hazard. The body itself is another. That silence has been the last item in a long inventory. Dust that embeds itself in lung tissue and never leaves. Radiation passing through walls without announcing itself. Solar storms arriving in under 30 minutes with doses that can kill. Temperature swings that crack metal and freeze lubricants into solids. a world actively shrinking and cracking along fault lines that run directly beneath the sites we have chosen. Moonquakes that ring for over an hour, backing out bolts and shifting foundations one vibration at a time. Micrometeorites striking every exposed surface without pause, year after year, stripping away thin layers of everything we build. A South Pole that concentrates every one of these hazards and adds several it keeps entirely to itself. And a psychological environment that quietly reshapes the people living inside it in ways engineering drawings do not capture. That is what we now know about the moon. So the question becomes unavoidable. Should we go back? The honest answer is that anyone who responds to that question with immediate certainty in either direction is not reckoning fully with what the evidence shows. This is not a scientific question, not really. The science describes the hazards. It maps the fault lines, measures the radiation doses, models the thermal cycles, catalogues the dust grain geometry. But the question of whether to go back is a human question. It is a question about what we are willing to risk, what we believe we are capable of solving, and what kind of species we have decided to be. Both sides of that question deserve an honest hearing. The case for caution is real and serious. The moon is genuinely dangerous in ways the Apollo program never revealed, not because the program failed, but because the stays were so brief that the hazards never had time to accumulate. 3 days on the surface is not enough time for dust exposure to reach clinically significant levels. It is not enough time for radiation dose to approach thresholds that produce neurological effects. It is not enough time for thermal cycling to fatigue a seal into failure, or for moonquake vibration to work a bolt loose, or for micrometeorite abrasion to meaningfully thin a habitat wall. 3 days tolerates a level of uncertainty that months and years cannot. There is no established safe exposure limit for lunar dust in a sealed habitat over extended stays. Not a provisional one, not a conservative one pending further study. None. The chemistry of South Pole crater dust has never been analysed. We have selected landing sites in terrain whose dust has never been touched by sunlight, and we do not know what disturbing it will release. Radiation poses a measurable cancer risk that increases with every additional week on the surface, and animal studies suggest possible cognitive and neurological effects at dose rates, consistent with long lunar stays. Solar particle events are unpredictable, potentially lethal, and capable of arriving in under 30 minutes. The warning systems and shelter designs intended to protect against them have not been tested in actual lunar conditions. They exist on paper and in laboratories and in proposals, not yet on the moon. Thermal cycling at the scale required for a permanent base has not been proven solvable. Moonquake risk at the South Pole is real, confirmed by research published in 2024 and 2025, and we have not completed the seismic mapping that would tell us whether our chosen landing sites sit on active fault lines. There is no working seismometer on the lunar surface right now. Not one. We are planning to send long-duration crews to a seismically active world with no real-time monitoring capability. These are not arguments against going to the moon. They are arguments against going to the moon the way we went in the 1960s and 1970s. Quickly, briefly, without fully understanding what we were walking into. The Apollo program was an extraordinary achievement that accepted extraordinary uncertainty because the stays were short, the program was singular, and the crews came home before most hazards had time to matter. That uncertainty is not acceptable for permanent presence. The stakes are different, the timescales are different, the failure modes are different. The cost of being wrong is not a mission that ends early. It is people who do not come home. But here's where it gets strange. The case for going is built on exactly the same evidence. Every hazard we have described is a known hazard, and that matters more than it might first appear. The dangers we cannot name are the ones we cannot engineer around. The dangers we have named, mapped, measured, and modeled are, in principle, solvable. The precondition for solving any problem is knowing it exists. Dust can be managed. Proper filtration systems, sealed airlocks, suit designs that prevent contamination from crossing into living spaces. These are not theoretical concepts. They are engineering problems. And engineering problems have solutions when people are motivated to find them and honest about what needs solving, rather than working around inconvenient complications. Radiation has genuinely promising directions. Regolith shielding is effective against solar particle events and reduces secondary particle production better than metal does. Habitats buried under 2 or more meters of lunar soil receive meaningfully lower doses than surface structures. The shielding is already there, on the surface, in essentially unlimited quantity. The challenge is building and deploying the systems to use it. Thermal cycling is a hard engineering problem, not a simple one, but engineering problems of comparable difficulty have been solved before when the motivation was sufficient. Moonquake risk can be meaningfully reduced through careful site selection informed by seismic mapping we now know we need, through better early warning systems, through habitat designs with flexible foundations and regolith coverage that absorbs sustained vibration rather than transmitting it directly into structural joints. Serious research is exploring all of these directions, and the reason to accept those engineering challenges is not abstract. The South Pole water ice, in the quantities current orbital data suggests, would change the economics and logistics of space exploration in ways that are genuinely difficult to overstate. A self-sustaining water source on the lunar surface means drinking water without launching it from Earth. It means breathable oxygen without carrying it from Earth. It means rocket propellant, hydrogen and oxygen both, produced locally rather than lifted out of Earth's gravity well at enormous cost per kilogram. The moon stops being a destination and becomes a waypoint, a refueling and resupply point for missions to Mars and beyond. The architecture of the entire future of human spaceflight shifts when the moon can supply itself. The scientific value compounds on top of that. The permanently shadowed crater floors preserve a record of the early solar system locked in ancient ice and surrounding rock, material that has been held in unbroken cold since before complex life appeared on Earth. The knowledge stored in that record is the kind that rewrites textbooks, not updates them, rewrites them. So here is the honest mid-2020s assessment, as Artemis prepares to return the first humans to the lunar surface since 1972. We are closer to ready than we have ever been. We are not yet fully ready. We have identified the dangers. We have not yet solved all of them. We have designs for better suits, better habitats, better radiation monitoring systems. We have not yet tested all of those designs in the actual environment where they will need to perform. We have selected landing sites. We have not yet completed the seismic mapping that would confirm whether those sites are geologically stable. We are moving in the right direction. We are not moving as carefully as the full weight of what we now know would seem to demand. That gap between the dangers we have described and the preparation we have completed is not a reason to stop. It is a reason to be honest. The moon will not forgive the same confident haste that worked for 3-day visits. What comes next will require something the Apollo era, for understandable reasons, never fully developed. Not just the engineering to keep people alive, the honesty to reckon clearly with everything trying to kill them. That honesty is where preparation begins. I said step back from the schedules for a moment. Step back from the landing sites and the engineering reviews and the budget timelines. Step back from all of it and look at the time the moon itself keeps. 4 billion years. That is how long the moon has been there. It formed from the debris of a catastrophic collision between the early Earth and a planet-sized object that no longer exists anywhere in the solar system. Gone completely. The moon is what survived. And in the 4 billion years since that formation, it has been shaped by things that do not hurry. Bombardment from the early solar system, raining down for hundreds of millions of years. Volcanism pouring ancient lava across its lowlands until the interior cooled and went quiet. Slow contraction as that interior shrank, cracking the crust from below. And the patient. Ceaseless work of solar radiation and micrometeorites, grinding the surface grain by grain, year by year, into the fine grey layer that covers everything. 4 billion years of that work, and the moon is still there. Think about what the moon watched during those 4 billion years. It watched the first single-celled life appear on Earth. It watched the oceans fill and empty and fill again. It watched the dinosaurs rise and move across a planet they owned completely. And then it watched them fall. It watched our earliest ancestors stand upright on the African savanna and look up at it for the first time, and begin, in whatever small way they were capable of, to wonder. It has been watching us our entire existence. Every generation of human beings who has ever lived has looked up at the same moon, casting the same light, keeping the same patient silence. It has never been in a hurry. It will not start now. We are the ones who are in a hurry. And that asymmetry matters more than almost anything else in this entire conversation. The dust is not in a hurry. The radiation is not in a hurry. The moonquakes are not in a hurry. The thermal cycles grinding slowly through every bolt and seal and weld are not in a hurry. They are all still there, exactly as they are, waiting. They will be there if we arrive in a year. They will be there if we arrive in a decade. They will be exactly as patient and exactly as dangerous, regardless of what a budget cycle demands or what a political timeline requires. The only question is whether we arrive prepared for what they actually are, or whether we arrive prepared for what we imagine them to be when we are moving too fast to look carefully. Going back to the moon is worth doing. That has to be said plainly and without qualification. It may be one of the most important things our species ever does. The scientific record locked inside those permanently shadowed craters, the water ice that could change the economics of everything that comes after, the knowledge waiting in that ancient undisturbed terrain, the possibility of what the moon could become as a waypoint for everything farther out. All of that is real. All of that matters. But doing it well means doing it honestly. It means looking at the grey surface of that ancient world and seeing it as it actually is. Not as the conquered stepping stone of the space race, the proof of human supremacy over distance and cold and vacuum. Not as the romantic silver companion of 10,000 poems, serene and welcoming and pale in a dark sky. Those are two versions of the same comfortable fiction. The moon is neither of them. It is a real place, a complex place, a dangerous place, a place whose dust has properties we have not fully measured, whose seismic activity is more widespread than we assumed 50 years ago, whose radiation environment asks more of us than 3-day visits ever revealed, whose thermal cycles destroy materials at timescales that short missions never witnessed, and whose South Pole, the very destination we have chosen, compounds every one of those hazards with several it owns alone. A place that will demand the very best of our science, and engineering, and psychology, and judgment. And that will give nothing back to those who arrive having underestimated it. The moon is patient. It has always been patient. And here's the thing about patience. It does not reward haste. It does not penalize caution. It simply continues at its own pace, with its own processes, indifferent to how quickly we decided to come back or how much confidence we brought with us when we landed. The only question that has ever really mattered is whether we are patient enough to deserve it. Let that settle for a moment. The numbers from this conversation, the orbital measurements and seismic magnitudes and temperature floors and particle velocities, all of it can drift now. The way sediment drifts down through still water and comes to rest at the bottom without urgency, without sound. The fault lines under the South Pole craters. The levitated dust that moves with the Terminator. The cosmic rays threading invisibly through rock. The thermal cycles pulling at every joint. Let them settle. They are real. They will still be real when the crews arrive. The question is whether the crews arrive knowing them clearly. The moon is still outside your window tonight, if you have one facing the right direction. The same light it has always cast. the same patient silence. It looks the same as it always has, but you see it differently now. And that difference matters, not because it makes the moon less beautiful. Knowledge does not make the universe smaller or less beautiful. It makes it more real. And more real, even when more real means more dangerous, is always better than the comfortable version of a thing never fully understood. We are standing at the beginning of something, not the end of preparation. The beginning of honest preparation. The kind that starts by looking clearly, speaking plainly, and moving at the pace the place itself demands. Rest. The moon will be there when you wake. So will the questions worth asking.